Hey guys, welcome back. Today we'll be starting a new chapter, General Mathematics. In this chapter we will go through the basics of Wavy Curve Method, trigonometric inequalities, modulus function, logarithms, greatest integer and fractional part, and some examples. So first let's look at Wavy Curve Method. This method is also called as method of intervals. So let us see what a wavy curve actually is. Wavy curve is nothing but it's a series of alternating peaks and valleys. You know, in maths, everything is a curve, and all the curves are used in algebra and calculus. So, a wavy curve means it is a series of alternating peaks and valleys. So, let us see some examples. Consider the function y equal to x minus 1 whole square. If you plot the graph, this will be something like this. The plot of y equal to x minus 1 would be something like this. This will be x equal to 1, and this will be y equal to x minus 1. As you can see, this is a curve with some peaks and some valleys. Okay, so can we say this is a wavy curve? Let's look at it. Consider one more function y equal to x minus 1. If you try to plot y equal to x minus 1, it would look something like this. At x equal to 1, the value is 0, and at x equal to 0, value is minus 1. So it would be something like this. Is it a wavy curve? Definitely not, as it has no peaks and valleys associated, and it is a continuously increasing function. So I think it might be clear till now that if for a function to be a wavy curve, it should be having some waves, right? So some positive, some negative, some zeros. Now look at plotting a graph. So generally, why do we use a wavy curve? Wavy curve is used to analyze the function without actually drawing it. Let us see how to do it. Consider this function y equal to x minus 1 times x minus 2. So as you can see, if I put x equal to 1, this function will be 0. And if I put x equal to 2, this function will be 0. That means the function is 0 at x equal to 1 and at x equal to 2. I know that at these values of x, the function will touch x-axis. But I don't know how the function would look like. But if you have some knowledge about drawing graphs, you can guess that the curve would be something like this. But since it is a simple function, it is a simple parabola, we know how to draw the function. And we can analyze what part of the function is positive and negative. You can see the part of the function which is left to 1 is positive, and the part between 1 and 2 is negative, and the part of the function which is after 2 is again positive. So, you know, as it is a simple parabola, we were able to analyze the function as it is very simple. But what if the function is not a very simple one? What if the function has very complex? Let us look at it. But before that, why do we use wavy curve? Wavy curve is used to solve inequalities in general. What is an inequality? An inequality is a comparison between two numbers or two mathematical expressions. That comparison can be less than or greater than or equal to. Let us look at what are zeros and poles before diving into solving these inequalities. A quick what zeros and poles are. Zeros are contributed by the numerator, and poles are contributed by the denominator. The value of the function at poles at zeros is 0, and the value of the function at poles is not defined. And these poles are also called as points of discontinuities. The zero which is contributed by the function or the part of the numerator which has odd powers is called a simple zero, and if the zero is contributed by the function which is having even power, then it is called a double point. We generally represent poles by using holes in the number line. We will look at it. Let us look at the example. We have to solve the inequality y of x greater than 0, and y of x is given as this. You see, this is not a simple function to plot, but we have to find at what values of x the function is greater than 0. As you can see, the zeros of the function are x equal to 1 and x equal to 2 and x equal to 3, and x equal to 4, the denominator is 0 and the function is not defined. Now let us try to analyze the equation. This was the given equation, these are the zeros. Let us draw the coordinate system first, and let us plot the zeros. So this is 1 and this is 2 and this is 3. So I can see that zeros divide the Cartesian plane into 4 quadrants. First quadrant, second quadrant, third quadrant and fourth quadrant. So now these are the 4 possible quadrants divided by the zeros. Now I have to analyze what is the value of function in each of these quadrants so that I can cover all the complete Cartesian plane. Now I want to know how the graph looks like or what is the value it takes left to x equal to 1. So for that, what I'm saying is I take an obvious point x equal to 0 and try to substitute in the equation y of 0. That would give me 1 by 2 or 1 2 3 6 by 4, that is 3 by 2, that would be 1.5. So this is positive. That means the value of the function which is left to 1 is always positive. So it should be always above the x-axis, and the value of the function between 1 and 2 would be negative. Since we are talking about linear functions which are having only power as even as odd, so if you know the sign of the function on the one quadrant, you can directly draw the actual function, just by doing this. Left of the 1 is positive and at 1 it is 0, and between 1 and 2 it should be negative as there should be continuity, and at 2 it is again 0, and again at 3 it should be 0 again, so like this, and again going. So this is how the function would look like. So it is so possible that the function might look like this also. There can be more like this, it can be like this, but all in all we want to know how the function looks like, or what is the sign of the function. So if I plot the function in actuality, so this would look something like this. So this is the actual function that would be looking like this. So here we have approximately plotted the exact function.